Welcome, learners. Robert Weissert here with another AP Statistics video. We're going to be covering experimental design. This will be a two-lesson set of videos. So this video will cover lesson number 1. Let's begin. If you're using the Practice of Statistics updated 6th edition textbook, you can find the material from that textbook in sections 4.2 and 4.3 that deal with this lesson. And if you're in AP Classroom, you'll find this stuff in Unit 3, topics 3.5 through 3.7. Let's begin. This lesson has a lot of vocabulary, so we'll briefly discuss that, but it's more important to know how to use that vocabulary in the context of a problem. So in trying to determine some sort of cause and effect relationship, the only way we can truly determine that is if we have some sort of experiment. And so as far as setting up experiment goes, we have to be able to give different groups some sort of treatment and make some sort of comparison. So you'll see in an experiment words like treatment, and treatments are things that are we impose upon subjects like people or some sort of inanimate objects in some cases, where we try to see if we can show that something causes something to occur. For instance, if we take a drug, we want to see if it causes people to respond to that drug, such as a heart medication or whatnot. Experimental units don't have to be people, but usually they are. And if they are people, then we tend to call them subjects. And a placebo can be a form of a treatment that has no effect, because naturally, when we take a pill or we do something that we think might cause something to happen, even if it is benign and doesn't really have that cause, our bodies react to that, and it has something called a placebo effect. So we tend to give at least one group, even if there's only one real treatment, another fake treatment, if you will, and we call that a placebo, to see kind of how to balance out the levels of differences. And within a treatment, you're going to see things called a factor. And a factor is basically an explanatory variable that's manipulated. It could cause a change in the response variable, what we're trying to measure. And within that factor, we have things called levels. And we'll get more into that, how some of the problems are laid out. So let's look at an example. All right, example 1. Have you ever dropped a tasty piece of food on the ground, then quickly picked it up and eaten it? You know, the 5-second rule. If so, you probably thought that 5-second rule, which states that a piece of food is safe to eat if it's been on the floor for less than 5 seconds. The rule is based on the belief that bacteria need time to transfer from the floor to the food. Does this work? Researchers from Rutgers University put the 5-second rule to the test. They dropped pieces of food onto 4 different surfaces: stainless steel, ceramic tile, wood, and carpet. So let's kind of analyze that for a second. We have 4 surfaces. We have stainless steel, ceramic tile, wood, and carpet. Waited for 4 different lengths of times. So we have less than a second, 5 seconds, 30 seconds, and 300 seconds. Finally, they used bacteria prepared 2 different ways: in a tryptic soy broth, whatever that is, and peptone buffing. Once the bacteria were ready, the researchers spread them out on different surfaces and started dropping the pieces of food. After waiting the designated amount of time, each piece of food was removed, blended, and plated on tryptic soy agar to allow bacteria to grow. So we try to put it all to the test to see what kind of treatments I could apply and make those comparisons and see if that 5-second rule actually works. So let's look at how to set up and identify all those treatments, explanatory variables, response variables, etc. Part A, what are the experimental units in this experiment? Well, in this case here, what are we trying to test? We're trying to test the pieces of food. We're seeing if there's bacteria forming up. So the experimental units aren't people in this case, they're not subjects, they're just pieces of food that we're measuring bacteria growth on. What about the factors in this experiment? The number of levels on each factor. Well, in this case here, we have a type of surface, that's kind of a typo here, type of surface, 4 levels, amount of time, 4 levels, method of bacterial preparation, 2 levels. So a lot of different ways to combine those. Let me make that typo there because it's really bugging me. So we'll say type of surface, 4 levels, amount of time, 4 levels, and 2 levels. And what we want to try to figure out is how many different ways are there to combine those and measure each one and make those comparisons. And so that's getting into every different possible combination. If the researchers used every possible combination of levels to form the treatments, how many of those could we include in the experiment? Maybe somewhat impractical to do all these, but if we could and use every possible type of experiment, how many would there be? Easiest way to do that is just multiply them together. Now we have four levels of surface, 4 levels of amount time, and bacterial preparation. So that's actually 4 times 4 times 2, which is 32 different treatments. So we could theoretically have 32 different ways to compare the things and see which one gives the most amount of bacteria. Finally, at the end, what are we trying to measure? Well, we're trying to measure how much bacteria growth on the food occurred. So what are two of the treatments? Because we're not going to list here all 32 possible treatments. Well, there's lots of different ways. Here's a couple examples I have. We have the stainless steel, less than 1 second, and tryptic soy broth. Notice that these are the three things we have to do. We have to determine the surface, the amount of time, and the type of bacterial preparation that we're doing. So in this case here, we have wood, 300 seconds, and peptone buffer. So those are two different type of treatments, but there's 32 combinations of treatments you could do easily. So you could list your own if you wanted to. Okay, this is a check your understanding. You might want to pause the video, see if you can read through this and try it on your own. I'll do the reading right now. Does the color of the restaurant server's lipstick affect how much customers tip? To find out, Lexi wrote red on 30 slips of paper and neutral on 30 slips of paper, mixed them well. Each time she got ready for work, she randomly selected one piece of paper to determine what lipstick color she would wear that day. The mean daily tip amount was $23 greater when she was wearing red lipstick. Identify the explanatory and response variables, the experimental units, and the treatments. So give it a pause, see if you can answer those, and unpause it, and we'll check them together. All right, we're going to answer this now. So let's talk about the explanatory variable. Of course, it's the lipstick color. That's what we're trying to change here. The response variable is going to be how much money we're going to get, the tips. So is the lipstick color going to affect the amount of tips? Response, that's our response. The experimental units are work days. Remember, we're doing this on randomly selected one piece of paper to determine what lipstick she would wear that day. So we're not testing it out on people necessarily. We're trying to see how much money we're going to make in that day. So the work days in this case would be considered the experimental units, if that makes sense. And the last part here, the treatments were either the red or the neutral lipstick. So that's how to identify those. Let's move on to the next part of the lesson. Okay, in this part of the lesson, we are going to just kind of go over this scenario here. So let's read through it. Questions, the scenario says, does caffeine affect pulse rate? In the next lesson we do together, we're going to actually have a little experiment with it. So does caffeine affect pulse rate? Many students regularly consume caffeine to help them stay alert. I know I do. So it seems plausible that taking caffeine might increase the individual's pulse rate. Is this true? One way to investigate this claim is to ask volunteers to measure their pulse rates. Now we're measuring, if we're asking volunteers, remember, we can't make people do something. So a lot of times we can't random sample for experiments. So we're only looking at people that are similar to ones that are like this experiment. Volunteers to measure their pulse rates, drink some cola with caffeine, measure their pulse rates. Again, after 10 minutes, calculate the increase in pulse rate. The experiment has a very simple design. A group of subjects, the students, were exposed to a treatment with cola with caffeine, and the outcome, change in pulse rate, was observed. Here's the design. We get a bunch of students. We give them some caffeinated cola, and we measure their pulse rate, do it before and do it after, see that change. Unfortunately, the pulse rates, for every student went, even if the pulse rate goes up, we can't necessarily increase that to caffeine. Maybe they're hyped up about the whole experiment and just they think they got it in their head that they're going to be more excited. They're going to have a higher pulse rate. Maybe the sugar in the cola is affecting it. We don't know. Okay. So what we're going to be doing is we're going to have some sort of control group that doesn't receive the caffeine. So I want you to think about what kind of a control group could we compare the caffeinated cola with to see, if there is an actual effect from the caffeine, because we don't want to just give a bunch of people caffeinated cola and see how that affects people. We want to have a comparison group, okay? And so that gets into the idea of something called control. So a control group is exactly what that is. A lot of times it's a placebo group or just a group that we're kind of holding in place, but they think they might be getting a treatment, but in reality, they're just getting nothing, like a sugar pill, or maybe the cola would be uncaffeinated. So in this case here, the non-caffeine, they're not just getting nothing. They're getting something that they think is affecting them, like caffeine-free cola. And then we can get a baseline. We can compare it to the two. So let's talk about how to word that in a problem. Let's look at example 2. Malaria causes hundreds of thousands of deaths each year, with many of the victims being children. Will regularly screening children for the malaria parasite and treating those who test positive reduce the proportion of children who develop the disease? Researchers worked with children in 101 schools in Kenya, randomly assigning half of the schools to provide regular screenings and follow-up treatments to their students, and the remaining schools to provide no regular screening. Children at all 101 schools were tested for malaria at the end of the study. We want to explain why it is necessary to include a control group of schools that didn't provide regular screenings. So I said, first thing is we want to have some sort of baseline. So one of the most important words on this is getting a baseline. We want to have some sort of way to compare them to begin with. The next thing is the purpose of that control group, or why is it necessary to do that? Researchers wouldn't be able to determine if a decrease in malaria rates was due to the treatment or some sort of other confounding variable, such as maybe drought or things that might naturally kill off mosquitoes, thereby naturally lowering the cases of malaria. So if we have a control group to be able to compare those two, then we wouldn't necessarily have to worry about confounding variables as much. We'd already hinted at the idea of a placebo, and that's having something where, like a sugar pill or a caffeine-free cola, where somebody thinks they're getting the medicine or the treatment, but in reality, they're getting really nothing. And the natural effects that your bodies react to that placebo is called the placebo effect. Now, that's one method of control, but also another couple of different methods of control is to blind the study. So you could have a couple different types of blindness. You might only single blind the study where maybe only the people that are receiving the cola know that or don't know that they're getting the caffeine-free cola. And maybe the researchers know, hey, I know who's getting the caffeine-free cola and I don't. But if truly the researchers don't know and the people that are subjects in the experiment don't know, that's what we call a double-blind experiment. And that might be helpful because there could be some bias imparted from the researchers giving a treatment to some sort of subject. So if there's people behind the scenes saying, all right, hey guys, give these people this without the people knowing what they're giving or getting, that might help reduce any sort of variability in the bias, okay? So let's look at the next example. Early researchers showed that magnetic fields affected living tissue in humans. Some doctors have begun to use magnets to treat patients with chronic pain. Scientists wondered if this type of therapy really worked. They designed a double-blind experiment to find out. A total of 50 patients with chronic pain were recruited for the study. A doctor identified a painful site on each patient and asked the patient to rate the pain on a scale from 0, mild pain, to 10, severe pain. Then the doctor selected a sealed envelope containing a magnet at random from a box with a mixture of active and inactive magnets. The chosen magnet was applied to the site of the pain for 45 minutes. After being treated, each patient was asked again to rate the level of pain from 0 to 10. The first part is we want to know, what does it mean for this experiment to be double-blind? And remember, a double-blind experiment is the researchers and the subjects don't know what treatment's being given or received. So neither the subjects nor the doctors applying the magnets and recording pain know which subjects had the active magnets and which had the inactive. Why is that important? Well, if subjects knew they were receiving an active treatment, researchers wouldn't know if any improvement was due to the magnets or to the expectation of getting better, placebo effect. If the doctors knew which subjects received which treatments, they might treat one group of subjects differently from the other. After all, we're humans. This would make it difficult to know if the magnets were the cause of any improvement. The idea is to rid this experiment of any sort of human bias that might influence the results at the end. Now, when conducting an experiment, you must randomly assign your treatment groups. You can't let them pick. You can't just say, all right, you have to go here, you have to go here. We have to be able to balance out the effects of other things that might cause influences in the response. So we want to have roughly equivalent groups to be able to do that. The only way to do that effectively is through random assignment. Now, the experiment that we're working on, and most of the times you're going to see, is something called a completely randomized design. It's similar to the SRS from sampling, but this is dealing with experiments. So the completely randomized design, don't abbreviate it, no CRD, is essentially everybody's in a pot. Okay, we got our volunteers for our study. We randomly assign one group, hopefully half to one group, a treatment group. The other half will go to the other treatment group, and we can compare those. So in the case of the caffeine and no caffeine, you got 20 volunteers. You would want to put all their names in a hat or use a random number generator, shuffle them up real good, randomly pick out 10 without replacement. Put those first 10 in, let's say, the caffeine group, and then the remaining one are going to go in the no caffeine. And then at the end, we can compare, measure their pulse rates and compare, is there a significant change? And then, and only then, if we do that random assignment, can we conclude there's statistically significant results if we see it. All right, here's a COVID-19 example. This is some recent stuff. Before making a vaccine publicly available, pharmaceutical companies must conduct well-designed experiments called clinical trials to demonstrate a vaccine's effectiveness and safety. Some of the most important clinical trials in recent years were the various COVID-19 vaccines. In Pfizer's clinical trial of its COVID-19 vaccines, half of the 43,548 volunteer subjects, it's a pretty big experimental trial, were randomly assigned to receive 2 shots of the vaccine 21 days apart. I remember getting that shot. The other half of those volunteers were randomly assigned to receive 2 shots of the saline placebo. So we have saline placebo and vaccine, and we have 2 different groups. After several months, Pfizer determined that its vaccine was 95% effective in preventing COVID-19. So you have the idea of that experiment. 43,548 people is a lot of volunteers. So I don't think putting all their names in a hat is probably the way that they went about separating them. They most likely did a random number generator or used a spreadsheet to help balance them out. In any case, let's look at how to set this up. So first part is, how could they have randomly assigned the 43,548 subjects to the 2 treatments in a completely randomized design? Easiest way to do it is a random number generator. Use Google, use a spreadsheet, use your calculator. And we want to get about half. So notice that I have the first half, 21,774, assigned different integers. Everybody's labeled 1 to 43,548. Easiest way to do it is alphabetize them in a list and randomly shuffle them and pick the first 21,774 that come up and assign those to the vaccine. The rest are going to get the placebo. The next part, explain the purpose of random assignment. And the reason we random assign is to have roughly equivalent groups. You don't want the volunteers to say, I'm going to go ahead and take the vaccine. And those 21,000 people are, if they're wanting to use the vaccine, they're not hesitant about it, there's no little qualms or anything, then they're more likely to probably respond okay to them. Whereas there might not be some adverse effects, but if you have all of them in a pot, you can kind of measure that, see the effectiveness a little better. So we want to create 2 groups that are roughly equivalent. Again, the most important thing is just 2 equivalent groups in terms of COVID-19 susceptibility before treatments are assigned. This is going to allow the researchers to make cause and effect conclusion. If you don't randomly assign them, can't do cause and effect. They can be volunteers, but you have to randomly assign. So in experiments, we want to be able to make sure we have enough people. So 43,000 people in a vaccine studies, a pretty good start. It does not have to be that big. But the idea is we want to have replication. We want to be able to give enough people, enough subjects, enough treatment groups, enough experimental units, I guess, to be able to get good data. And we want to also have control. Control can mean a control group. There's other ways that we'll talk about control in another lesson. But for right now, like a placebo or anything that we can make sure that their variables are constant. For instance, maybe if we're doing a drug trial, all the people in that trial are very similar. For instance, adult men who might react the same way to the drug. Therefore, we can eliminate any variation in the type of person taking the drug and just focus on the effects of the drug itself. Let's talk about the caffeine versus pulse rate experiment. Um, if we're talking about if we keeping the amount of soda constant, in other words, if we give everybody the same amount of soda, we might see a bigger difference in the results. But let's say somebody in the group just drank a whole 2 liter of caffeinated, soda, and one person in the caffeine group drank just a cup of it. Are there going to be big differences in the amount of caffeine they drink? Absolutely. So we want to be consistent when adding control. So it doesn't always have to be a placebo group when I'm talking about control. It means making sure that there's a lot of consistency when you're giving those treatment groups. Along those same lines, control essentially just helps confounding be reduced. Might not eliminate it, but confounding, remember, is when you don't know what's actually causing the variables to change. Control can help reduce that. And it also reduces variability in the response variable. Like we said before, if we give everybody the same amount of cola, we might not see as big of a variability in the difference between the caffeine groups within the caffeine and the non-caffeine groups within that group. So we can better easily determine if one treatment is more effective. Example 5, researchers in Canada performed an experiment with university students to examine the effects of multitasking on student learning. I know I'm terrible at that. The 40 participants in the study were asked to attend the same lecture and take notes with their laptops. Half of the participants were randomly assigned to complete other online tasks not related to the lecture during that time. These tasks were meant to imitate typical student web browsing during classes. The remaining students simply took notes with their laptops. At the end of the lecture, students were given the same test about the content of their lecture. You can think about that for a second. Let's answer a couple questions. Let's identify 2 variables that the researchers kept the same during the experiment. Can you think of any? Well, first thing is all the students attended the same lecture and they were given the same test. That way we can control the variation in what they know, based off of what they were doing while they were sitting in class. We could only focus on the things that were changing their note-taking abilities in class based on their browsing habits. A lot of you probably do a lot of things on your phone when you're learning, and I know that affects me when I'm learning or trying to focus on something. So I can see that being some sort of thing that would influence the results. Let's describe a benefit of keeping these variables the same. While students attended different lectures or took different tests, the test scores would likely be more variable. What if some groups of students had an easy test, some had a hard test? How can we compare those test scores? So we want to be able to keep those things the same. Same lecture, so that way the same professor, they're getting the same content, same information, so they can better compare the growth on their test. This increase in test score variability would make it harder to find convincing evidence that multitasking is harmful. So we want to reduce that variability by keeping it the same. So to kind of wrap things up, experimental design has 4 key components. Comparison. We want to be able to have at least 2 things to compare. So a control group and a new treatment to compare. You definitely can have more than 2. You can have 32 treatments, as we found out in one of the examples. Random assignment, so we can show cause and effect. Replication. You want to have enough people to be able to make this worth your while. And control. Try to keep the variables consistent so we can reduce outside effects on your response. All right, this is a check your understanding. So I'll kind of ask you to pause within each part because they're going to display most of the screen there, so you won't see them all on one screen. Many utility companies have introduced programs to encourage energy conservation among the customers. An electric company considers placing small digital displays in households to show current electricity use and what the cost would be if this use continued for a month. Will the displays reduce electricity use? One cheaper approach is to give customers a chart and information about monitoring their electricity use from the outside meter. Would this method work almost as well? The company decides to conduct an experiment using 60 households from a small city during the month of April to compare these 2 approaches, the digital display and the chart. But most importantly, we want to have some sort of control because we think that those things might influence their electricity consumption. So we're going to have a group of customers who receive nothing other than information about energy consumption, but no help, no chart, no digital display, because we want to see if that information might just have some sort of baseline influence. So what's the importance of that? Pause it, see if you can write something. All right, in 3, 2, 1, we're going to display this. So I like to just say comparative purposes. We want a control group that would show how much electricity customers would tend to naturally use. So that's a baseline for us. This would serve as a baseline to determine how much less electricity is used in the other treatment groups, if at all. So again, keyword I kind of find is comparative, but I like to use that word baseline so we can kind of get a starting point. Part B, describe how to randomly assign the treatments to the 60 households. Well, we have really kind of 3 groups, right? We have the 2 treatment groups plus the control group. So display chart and just the information. So we're going to have to split this up into 20, 20, and 20 somehow. How would you do that? We could number them 1 to 60. You could put all their names in a slip of paper, put them in a container or a hat, shuffle well. You could use a random number generator if you like. So using the hat, just draw out 20 slips without replacement. The corresponding households are going to get the digital display. Put those aside. The next 20 slips you draw, if you mix them up, they're going to get the chart. And then the remaining ones will get only the information. That way you have your 3 groups that are randomized. What's the purpose of this random assigning treatments? Again, we want to have what? We want to have some sort of equivalent groups to be able to compare those to. So we're going to create groups of households that are roughly equivalent at the beginning of the experiment in terms of electricity usage. It's going to ensure that the effects of other variables are spread evenly among the 3 groups, allowing the researchers to make cause and effect conclusions. And lastly, what are some of the variables that we controlled for? So identify one variable that the researchers are keeping the same for experimental units. Let's look over here. Can you think of anything in here that we're kind of keeping very similar so that way we can control for outside variability? Well, I said a couple things. So I kind of wrote 2 things on here. You didn't have to do 2 necessarily, but what I said was customers were from the same town. So look at over here. If I said a small city, we only got information from those people because maybe in a larger city, the electricity rates would be different. People might not have different habits. And we also talked about, we did it just during the month of April. We didn't do some in April, some in July, some in November, because electricity can vary throughout the course of the year with the temperature. So this will help reduce that variation in electricity use. Well, I hope this was helpful. The next lesson that we do is going to cover the next part of experiments, so stay tuned for that. And our lesson summary, just a bunch of vocabulary and making sure we know how to write that into a free response item. So we got some keywords. We got explanatory versus response variables. Response is what you're measuring. Explanatory is what you can change. Confounded is when we have some sort of variables that might influence the response variable that are not accounted for. Treatments, experimental units, which oftentimes are subjects like people, levels, factors, how we can kind of split those up. The placebo effect and placebo, double blind versus single blind, having a control group or using some sort of control, and a completely randomized design being the type of experiment where everybody kind of gets put into a hat, and depending on your treatments, you randomize it and try to get equivalent groups within each treatment group, and then measure the results at the end. As far as the principles of experimental design, there are 4 of them. We have comparison. We have to be able to have different groups. Can't just do one thing. We have to have random assignment, so you can have cause and effect. Replication. We got to have enough subjects or treatments or both to be able to make this worth our while. And then finally, have some sort of control, whether it's a placebo group, we're getting the same types of subjects, using the same month for temperature, for example. Those are all things that help with control. So hopefully this was helpful, and I appreciate y'all watching. If you have any questions on your assignment, reach out. Have a great day, guys.